Mafia.
Talk shit, you gon' bust. Told yourself a million times you don't give a fuck. Sold over a million dimes hanging in the cut. Sold over a million dimes, I don't give a fuck. What?
Max.
All right, so when you're dealing with nuclear reactions, you're dealing with the things inside the nucleus. So protons and neutrons is what we're talking about mostly. And so sometimes when where too many protons are in the nucleus, it becomes really unstable, and it's going to want to actually release those protons. So when does that happen? All nuclei with more than 83 protons in the nucleus decay spontaneously. So they're actually going to automatically, without even doing anything, start releasing those protons and neutrons to make it smaller and a much more stable nucleus. So let's look at polonium. Not only does polonium right now, if you look at the neutron to proton ratio, it's actually okay. For higher atomic numbers, 84 is relatively high. 1.5 ratio for neutrons to protons is actually pretty okay. However, we have 84 protons within our nucleus. Not okay. Too many. So what's going to happen is it's going to release a helium nucleus. So it's going to release 2 protons and 2 neutrons to try and get that back down to something a little bit more stable. And it's going to, in this particular reaction, it's going to end up as lead 82. It's going to transmutate from polonium to lead. And let's look at the neutron to proton ratio for lead. This is 1.51. It might continue to decay. This actually is a little bit high. It's not crazy high, but a little bit high. So it might continue to decay. Because it's high, it might go into beta decay. But this might be stable enough to stay where it is. So notice also when you're dealing with nuclear reactions that the mass numbers have to equal if we're going to continue if we're going to say this arrow as an equals number, 210 is equal to 206 plus 204, and 84 is equal to 82 plus 2. So when you're dealing with nuclear reactions, make sure that your mass numbers equal up and make sure that your atomic numbers equal up also. But anything with proton over 83 is going to decay automatically, and that's called alpha decay, and it's going to release an alpha particle. All right, so when you're dealing with nuclear reactions or reactions that happen within the nucleus of an atom, there are several different types of reactions that can occur, one of them being beta decay. And this is when a neutron decomposes into a proton and an electron. Okay, so why does this happen? Well, the neutron to proton ratio is above the band of stability. And if I go over to the band of stability, over here, this is the black kind of grayish line. We want to make sure our neutron to proton ratio falls within that grayish line. If it doesn't, then something's going to happen. It's going to start radiating some sort of energy, and things are going to happen with the nucleus to make it more stable and to lie within the band of stability. Okay, so beta decay is when it's above the band of stability. So what happens then? Well, the neutron to proton ratio is too high. It's above the band of stability, meaning that there are too many neutrons. Okay, so we have to do something about that neutron, those neutrons inside that atom. Well, let's look at a stable atom. We know that carbon-12 has mass number of 12 and 6 protons. So our neutrons is 6 and our protons is 6, making a total mass number of 12. And our ratio is 1 to 1, which is what we like. We like a ratio of 1 to 1 at low atomic numbers. And carbon is a low atomic number, so it has a ratio of 1 to 1, so it's not going to actually undergo any sort of nuclear radiation. So it's totally okay, it's safe. But then you go over here to carbon-14, an isotope of carbon-12. Protons are the same, 6 protons, and then we have 8 neutrons. 6 plus 8 is 14. So our ratio, neutron to proton ratio, is 1.33, which is a bit high for atomic numbers of such a low magnitude of 6. So what we're going to have to do is get rid of some of those neutrons. So inside the nucleus, what's going to happen is one of the neutrons is going to decompose, and it's going to decompose into a proton and an electron. Notice that one positive one and a negative one are going to come together to make a neutral charge. So we have to make sure that these actually add up, and this making the yield sign an equal sign. So I might want to put that up there, just so we can be clear on what that means. Okay, so what exactly is happening? So if our carbon-14 with a mass number 14 and an atomic number of 6 is going to decompose, and this is going to happen, and it's actually going to emit this electron. So it's going to be a high-speed electron, and it's going to emit it into the atmosphere. Not only is it going to emit electrons in the atmosphere, which are pretty bad for the environment, pretty bad for us, but it can be blocked by things like foil or a thin material can actually block this, so it's actually not that damaging. But it does emit something into the atmosphere. It also emits high energy particles called gamma rays, just as energy, because this is coming from a high energy system. Now we're going to a low energy system, and the energy is going to be released as gamma rays. So that's actually what's dangerous about this radiation. Anyway, so it's going to go down to a nitrogen with a mass number of 14 and an atomic number of 7, so it's actually going to mutate from carbon to nitrogen. And let's look at this proton to neutron ratio, or this neutron to proton ratio. So the number of neutrons we have in here is 7. So we're going to look at our neutron to proton ratio for nitrogen. And we have 7 neutrons and 7 protons. So this is a 1 to 1 ratio. And so this is totally okay. So now we stabilize this carbon atom, and now it's going to be a nitrogen atom. So this is just one way that an unstable nucleus can actually start becoming more stable, is by emitting beta particles or electrons.
Max.